Alright, everyone. Today we are talking about section 10.8. This is actually the second time I've had to record this lecture because the first time I forgot to include volume. So, without further ado, let's talk about how to choose a convergence test. So, there are several questions to keep in mind whenever you're trying to choose the appropriate test for determining convergence or divergence of series. The first thing that you should always do is you should always check the divergence test first. The reason we always check this test first is because it's an easy thing to determine if the thing diverges. Specifically, if the limit as k approaches infinity of ak is not equal to 0, if it's literally anything else, then the series of k equals 1 to infinity of ak diverges. The second thing you might think about looking at is whether it's a special form. So if it's a p-series, a geometric series, or if it's telescoping, then you should consider using the technique specific for those types of series. Thirdly, if the series is a rational function, or if it looks like one, then you should consider using the limit comparison test. Limit comparison test, or the direct comparison test. Remember, as I told you in the last section, if we attempted to use the ratio or the root test for these types of series, we would get no conclusion. And so the limit comparison test and the direct comparison test are good ones to use for rational functions. Fourth, if the series contains negative 1 to the k, consider using the alternating series test. So remember that you don't need to use the alternating series test if we have negative 1 to the k. There are other options, most notably the ratio and the root test, or the divergence test. But if you do see negative 1 to the k, the alternating series test should at least be a strong option in your mind. Fifth, if the series contains a k to the k, a k factorial, or any factorial for that matter, or b to the k, where b is just some real number, like 5, 7, or 15, consider using the ratio or the root tests. So k to the k, k factorial, and b to the k are notorious for being things that are difficult to integrate. Sometimes it can be difficult to consider the limit, and comparisons can often be tricky. So especially if it contains a factorial, definitely consider using the ratio or the root test. And sixth, if none of the above options work and the function f of k equals a of k is easily integrable, so you can integrate it easily, consider using the integral test. That's normally a last resort for us, though. So here, a couple of years ago, I made a series test flowchart that kind of gives you an idea on when you should use certain series. So let me just go over this briefly. You can find the full file for this thing on Canvas if it's difficult to read on the slides. The divergence test is the first thing you should always look for. If the limit is not 0, then it diverges. Then you should check for special forms, p-series, geometric series, telescoping series. Then consider alternating series. In this case, we are going to define ak to be negative 1 to the k times bk. So whenever we did the alternating series test, we called ak everything except for that negative 1 to the k term. In this case, we are going to let that be our bk. The idea is that if bk is non-increasing and satisfies the limit as k approaches infinity of bk equals 0, and bk, if it satisfies these two things, then it will either converge, or it will converge absolutely, or it will converge. If it doesn't satisfy one of those two things, then it probably diverges, and you should consider doing the divergence test again. If it did satisfy those two conditions, non-increasing and limit was 0, and the sum from k equals whatever to infinity of bk, so that's just the positive part, the part that didn't include that negative 1. If this converges, then the series converges absolutely. Otherwise, if this does not converge, then we say that it converges conditionally over here. The next thing to think about is if it's not an alternating series or that test was inconclusive or something, we should consider using the ratio or the root tests. So there are no conditions beforehand that we need to check. We just need to use the ratio or root tests. In the ratio test, we define R to be the ratio of the k plus first term divided by the kth term, and we take the limit of the absolute value of that. And then in the root test, we define rho to be the limit as k approaches infinity of the kth root of the absolute value of ak. In either of these cases, if rho or r is less than 1, then it converges absolutely. If rho or r is equal to 1, then it is inconclusive. And if rho or r is greater than 1, then it diverges. Continuing, if that was inconclusive, we might consider using the direct comparison test. We're going to pick some bk, it's got to be positive, and we ask ourselves, does the sum of bk converge and satisfy this inequality? Sum of ak, or not sum of ak, is ak less than or equal to bk? If that is true, then it converges because the larger series converged, right? Because ak here is smaller and the sum of bk converged, so the sum of ak is smaller and must converge as well. Alternatively, if bk diverges and bk is the smaller series, then ak must diverge as well. If it doesn't satisfy those conditions, then it is inconclusive, and we got to try either another test or a different comparison. The limit comparison, remember, is the one that we like. This is the one that we use 95% of the time. The idea is that we define L to be the limit as k approaches infinity of ak over bk, where bk is the thing we're comparing to. We ask ourselves, does the sum of bk converge? If yes, and the limit is equal to 0, or it is between 0 and infinity, then the sum of ak converges. If the sum of bk diverges, and L is equal to infinity, or it is greater than 0, then the sum of ak diverges. If it doesn't fall into either of those two categories, then it is inconclusive and we're going to have to try another bk or a different test. And then finally, if all else fails, try the integral test. The thing that sucks about the integral test is we have to check 3 previous conditions. We have to check if it's continuous, if it's positive, and if it's decreasing. We have to define this function f of k equals ak, and then we have to actually compute an integral, an infinite integral for that matter, and that can sometimes be challenging. If the integral is finite, then it converges. If the integral is infinite, then it diverges. And if you can't integrate it, or if none of these techniques worked for you, then you're going to have to try something else. You're going to have to try one of these tests again. I assure you that any series that we come across in this class will be able to be tackled with one of these tests that we've come across so far. Alright, so next what I want to talk to you guys about is the series test summary sheet. You will get this sheet on the exam and on the final. So basically what it tells you is when certain series converge and when certain series diverge. So if you have a geometric series, remember that it converges if absolute value of r is less than 1, and it diverges otherwise. I'll let you read through the details on this sheet on your own, but just know that you get this entire sheet on the exam. Alright, so with the rest of the time, I just kind of want to do a few examples for you. Some of these appear on your homework, and so they're certainly prudent for you guys to keep in mind. So, without further ado, let's tackle some of these. The first series that we're trying to determine the convergence or divergence of is the sum from k equals 1 to infinity of 4 times 3k factorial divided by k factorial cubed. So this at first can seem a bit intimidating, but it's really not too bad whenever we notice the fact that there is a factorial here. And since there is a factorial, that tells us that we should use the ratio test. Not the root test, even, but use the ratio test here. So anytime you see a factorial, you will be using the ratio test. Alright, so let's try it. The ratio test requires that we define, I don't know why my pen's thick, let's give it a second. We're going to define AK to be 4 times 3k factorial over k factorial cubed. And we're going to define, not bk, sorry, we're going to define ak plus 1 to be 4. So every time we see a k in this expression, we're going to replace it with a k plus 1. So we have to put it in parentheses right here. And then we also see a k down here, so we're going to replace that with k plus 1. Once again, it's important that we replace it and put parentheses in. Alright, so that's our AK, that's our AK plus 1. We're going to define R to be the limit of their quotient. Alright, so AK plus 1, we have 4 times 3k plus 1 factorial over parentheses, parentheses, k plus 1 factorial, that thing cubed, times 1 over ak, which is going to be k factorial cubed divided by 4 times 3k factorial. So one thing you might notice is that there's a 4 on top and a 4 on bottom. Those cancel out. But everything else is a little bit more tricky to see, so let's go through that a little bit slowly. Alright, so on top we have 3k plus 1 factorial. We can rewrite that as 3k plus 3 factorial. And then we also have 3k factorial. Or sorry, that's not correct. We have k factorial cubed. On bottom, we have k plus 1 factorial cubed. And actually, one thing I want to write on top, instead of k factorial cubed, let's instead write that as k factorial times itself 3 times. So we're going to write it like this. K factorial times k factorial times k factorial. I think this will be illuminating here in a second. On the bottom, we have k plus 1 factorial cubed. And so we can write that as k plus 1 factorial times k plus 1 factorial times k plus 1 factorial. And of course we have this 3k factorial over here as well. Okay. So the next thing to notice is that 3k plus 3 factorial is really just 3k plus 3 times every integer smaller than it. So 3k plus 3 times 3k plus 2 times 3k plus 1 times 3k times every integer smaller than that. So we would say times 3k minus 1, 3k minus 2, 3k minus 3, all the way down to 3, 2, 1. Or we could just think of this as 3k factorial right here. And then we still have on top k factorial, k factorial, k factorial. Alright, and so we have a 3k factorial on bottom, And we also have k plus 1 factorial multiplied by itself 3 times. So each one of those could be decomposed into k plus 1 times k factorial, k plus 1 times k factorial, and k plus 1 times k factorial. And so now, hopefully you see some of the cancellations here. We have a k factorial here, and 2 more of those. We also have a 3k factorial and a 3k factorial here, and so that leaves us with the following. We have the limit as k approaches infinity, absolute value of 3k plus 3 times 3k plus 2 times 3k plus 1, all over k plus 1 times k plus 1 times k plus 1. Alright, so the next step here would normally be to expand out both the numerator and denominator, so that way we could take the limit. But if you can kind of see ahead a little bit, the idea is that we have to compare the powers of the numerator and the denominator. Notice that this is a rational function with a polynomial on top and a polynomial on bottom. So we only need to consider what the power on top and the power on bottom will be. The power on top will be, or the degree on top, I should say, will be 3, because we end up with a k cubed as our largest power. And similarly, on the bottom, if we multiply that all out, we would get a k cubed down there. Since these are the same, we have to consider the coefficients of these two terms. And so on bottom, the coefficient would just be 1, because each of these has a coefficient of 1, so 1 times 1 times 1 is just 1. And on top, we would get a coefficient of 27, because 3 times 3 times 3 is 27. And so this limit, overall, will just be 27 over 1, which is 27. And that is greater than 1. So we write our conclusion. Since r is equal to 27, which is greater than 1, the series sum from k equals 1 to infinity of 4 times 3k factorial over k factorial cubed diverges by the ratio test. Alright, so that's all we got to do. Next, we're going to determine whether this series converges or diverges. We have the sine squared of k divided by k to the 3/2 power. So, there are a few things to consider. First of all, if we started by trying to do the divergence test, we would actually get no conclusion. The reason being is because the limit of sine squared of k over k to the 3/2 power is just 0. And we can prove that with the squeeze theorem. And since that is 0, that leaves us with no conclusion by the divergence test. Alright, so what other things can we think about? Well, it's not geometric, it's not quite a p-series, it's definitely not telescoping, it's not alternating. We could try doing the root and ratio test, but I'll just tell you now that those are inconclusive as well. Integral test is pain, so we're not going to try it. And that only leaves us with a comparison test. And this is one of the few examples where actually a direct comparison test is preferable. And I'll explain why after we get through it. So this is the direct comparison test. And so the way that we use the direct comparison test, remember, we are going to define AK to be sine squared of k over k to the 3/2. And we are going to define BK to be the thing that we already know the behavior of. So we need BK to be something that we already know the behavior of. We need to know if it diverges or converges. And in this case, the thing that is proper to use is 1 over k to the 3 halves. This is something we already know the behavior of. We know that this thing will converge because it's a p-series where p is greater than 1. And when it comes to the direct comparison test, it actually works out pretty well. Specifically, we know that sine squared of k is less than or equal to 1 for all values of k, right? And so that implies that sine squared of k over k to the 3 halves is less than or equal to 1 over k to the 3 halves. And now suddenly, this is our ak and this is our bk. And our larger series converges, this bk converges, which means that our smaller one, ak, must converge as well. So let's write that down. So since ak is less than or equal to bk for all k from 1 to infinity, and the sum from k equals 1 to infinity of bk converges, because it is a p-series where p is equal to 3 halves, which is greater than 1. That means that the sum from k equals 1 to infinity of ak converges as well. By the direct comparison test. All right. So I told you at the beginning that a limit comparison test was probably not a good idea for this problem. The reason that a limit comparison test would ultimately not work is because if we were to use the same choice of bk, then what we would have to compute is this limit. The limit of ak over bk would be sine squared of k over k to the 3 halves times k to the 3 halves over 1. And so we would get the limit as k approaches infinity of sine squared of k. And I don't know what that is. In fact, this limit will oscillate forever between 0 and 1. And so we would just end up with no conclusion. And so this would cause us some problems. And so the limit comparison test ultimately would not be a good idea to use here. We instead would want to use the direct comparison test for a quicker reasoning behind this problem. Okay, let's try this one now. We have the sum from k equals 1 to infinity of negative 1 to the k times 5k squared over 3k squared plus 7, all raised to the k power. All right, so one thing you might notice is that there's this negative 1 to the k power out front, and so that might give us the inclination to use the alternating series test. Unfortunately, if we were to use the alternating series test, one thing that we would have to compute is this limit. We would have to compute the limit as k goes to infinity of 5k squared over 3k squared plus 7, all raised to the k power. And that can be done, but I think it's fairly challenging, and so perhaps you don't want to try that. So instead of the alternating series test, let's try and think of another idea. One thing that you might come across, or might notice, is that everything here is raised to the k power. So let's consider using the root test. So if we do the root test, we define rho to be the limit as k approaches infinity of the kth root of the absolute value of negative 1 to the k times 5k squared over 3k squared plus 7, all raised to the kth power. So one thing you might notice is that this negative 1 to the k disappears because we are inside of an absolute value. So the absolute value of negative 1 to the k is just 1. And so this whole thing is just equal to 1 inside of an absolute value. And then also, we have a kth root and a kth power that's just left, and so those will cancel out as well. This leaves us with the limit as k approaches infinity of the absolute value of 5k squared over 3k squared plus 7. At this point, I could drop the absolute value if I wanted to, because everything inside of the absolute value is now definitely positive, and it won't change the answer at all. But I don't need to. One thing I notice is that this limit has a numerator with degree 2 and a denominator with degree 2. Since those are the same, we consider the ratio of those coefficients, and in this case, that is 5/3. So, since 5/3 is greater than 1, this must diverge. So let's write that down. Since rho is equal to 5/3, which is greater than 1, this series diverges by the root test. Okay. And one thing I want to go back to this previous problem on is the fact that one thing they might ask you about is whether the thing converges absolutely or converges conditionally. This series will converge absolutely, and that's something I should probably say. It converges absolutely. I should say that here, absolutely. The reason it converges absolutely, remember, is that all we have to do is consider the absolute value around the series, and if that thing converges, then the series converges absolutely. But taking the absolute value around this guy doesn't actually change anything because everything's positive from the beginning. And so since nothing changed, everything was positive from the beginning, we know that it converges absolutely. The absolute value did not affect the series whatsoever. So that's just something to keep in mind whenever you're trying to write down something about convergence. The first and third examples we did both diverge, so those don't get affected at all. All right, next let's try this guy. We have the sum from k equals 1 to infinity of k plus 1 over the square root of 9k to the 6th plus 1. So we could start by considering the divergence test. If we take the limit of just this summand, we would get that the limit is equal to 0, which once again gives us no conclusion. So we should consider some other test. In this case, the best test to try is the limit comparison test. And the reason we know that the limit comparison test is preferable is because this thing looks approximately like a rational function. And since it is approximately a rational function, specifically the numerator looks like k and the denominator is the square root of k to the 6th, so we can just consider this as like k cubed. And so the thing to compare to would be 1 over k squared. So we are going to define bk to be 1 over k squared, and we're going to take the limit of ak over bk. Alright, so ak was k plus 1 over the square root of 9k to the 6th plus 1, and bk is 1 over k squared. So if we divide by it, we're really multiplying by k squared over 1. This gives us the limit as k approaches infinity of k cubed plus k squared divided by the square root of 9k to the 6th plus 1. Alright, so if you remember back from your days in Calculus 1, the trick for figuring out this series is to multiply both the numerator and denominator by 1 over k cubed. And so in the denominator, when we multiply by 1 over k cubed, what we're essentially doing is we are multiplying by the square root of 1 over k to the 6th. Alright, and since those are both in a square root, we can write it out. We can multiply the two things inside the square root. So in the top, we get 1 plus 1 over k. In the bottom, we get the square root of 9 plus 1 over k to the 6th. The limit of 1 over k is 0. The limit of 1 over k to the 6th is 0. And so we're just left with 1 over the square root of 9. Which is just 1/3. I really should omit the limit on this problem, so let me just write it like this. Alright, and since this is 1/3, so since, let me call this thing L. So since L is between 0 and infinity, the sum of AK and the sum of BK have the same behavior. Since the sum from k equals 1 to infinity of bk converges, it's a p-series where p equals 2, which is greater than 1. We conclude that the sum from k equals 1 to infinity of ak converges also. By the limit comparison test. Oof, really had to write a paragraph for that one. Alright, so that's a limit comparison test problem. Notice at the beginning it looked pretty similar to a rational function, and so that was the evidence that we needed to attempt a limit comparison test. Alright, so next we're going to consider this series. We have negative 1 to the k times k divided by k cubed plus 1. There are a few things you could think about here. One of the things to consider is the fact that if you were to try the divergence test, you would get inconclusive as an answer because the limit of this thing is 0. And if you take If you notice, we have a negative 1 to the k multiplied by our thing, and so maybe the alternating series test is a good idea. So let's give that a shot. So let's define AK to be k over k cubed plus 1. Then we have to ask ourselves two questions. One, is AK non-increasing? And remember that I told you there were two ways that we could do this. We could either show that AK plus 1 is less than or equal to AK, or we could take the derivative of the associated function. Specifically, that would be x over x cubed plus 1. And if that thing is negative, or I guess since it's non-increasing, it can be less than or equal to 0. If that is true, then it is non-increasing. In this particular case, I would argue that the derivative is the way to go, so let's just verify that. All right, so when we take a derivative, we're going to have to use a quotient rule here. So it's low d high less high d low. So low times the derivative of the top, which is just 1, less high d low, so 3x squared, divided by the bottom squared, so x cubed plus 1 squared. So on top, this simplifies to just be negative 2x cubed plus 1. And on bottom, we've got x cubed plus 1 quantity squared. So the question you have to ask yourself is this derivative less than or equal to 0 on 2 to infinity? So the reason we care about 2 to infinity is because our first index over here was 2. And so the range you can kind of think of the sum as is 2 to infinity. And indeed, this is true, because if you were to throw in a, if you were to throw in a 2 right there, then you would get negative 16 plus 1 as a numerator, and that's just negative 15, so that's negative. And for any larger value of x, it would be even more negative, which indicates that this indeed will be a negative value for any x that's between 2 and infinity. All right, and so this is indeed non-increasing, as we desired. And the second thing we have to do is we have to compute the limit. Specifically, we're going to take the limit as k goes to infinity of k over k cubed plus 1. And this, of course, is just equal to 0 because the denominator power is larger. And so, by the alternating series test, the series from k equals 2 to infinity, negative 1 to the k times k all over k cubed plus 1 converges. All right, so great. We determined that it converges. They might also ask us to figure out if this thing converges absolutely. So remember the thing that we do to test absolute convergence is we just take the absolute value inside our sum. And in this case, that's going to be sum from k equals 2 to infinity of k over k cubed plus 1. I got rid of the absolute value because after we get rid of that negative 1 to the k, everything else is positive. And this series will converge by comparison test. I'll let you work out the details, but yes, this would converge by, you could do a limit comparison test, and yeah, I'll just say it converges by limit comparison test. On an exam, you would be expected to work out the details here, but I will leave that to you to do. And so the primary conclusion is that since the original series, the one with that negative 1 to the k, and the absolute value both converged, the entire series is absolutely convergent. So therefore, the series k equals 2 to infinity of negative 1 to the k times k all over k cubed plus 1 converges absolutely. And we're done. So there are a lot of other examples to do for section 10.8. There are some in the learning activity that I will post to Canvas that I would highly recommend that you take a look at. And then there are also just a ton of problems in your section 10.8 of the textbook. So if you get super bored or you're worried about calculating series and you want to prepare for the exam, that is a good place to start. Just go to section 10.8 and try and pump out as many of those series as you can and see if you can determine whether they converge or diverge. Alternatively, if you don't want to do all of the arithmetic, you can just look at a series and then say, yes, I know that I need to use the divergence test for that one, or yes, I definitely need to use limit comparison for that one, or I need to use root or ratio. If you can at least identify which test you're using, that's half the battle. So I highly recommend that you give those some practice, and that's all I've got for Chapter 10. So we have learned all of the different techniques to determine convergence or divergence of series. In Chapter 11, we're going to start using some of these techniques in practical applications, which are really, really cool. And so, until then, I will bid you adieu, and I will see you next time.